Everyone know, Lidong has been kind enough to share his slides with us. So later, if you want to review the slides, you're more than welcome to. We're taking a recording with his consent. So if you have colleagues that aren't able to make it, or for whatever reason this room gets too uncomfortable and you want to leave, then you can watch it again later on. This seats over there. Okay. So. Lidong is the head of the Alibaba DAMO Academy here doing R&D in AI research in Singapore. And he's presenting a presentation that's a little bit more technical, geared towards our natural language colleagues, titled Text Generation, Editing, and Summarization. So while he has a very long biodata with many storied achievements, I think important, especially for PhD students, as of course they're hiring. So yes, please talk with Lidong. You have his email address from the talk information, and then you can reach him. They're looking for fresh graduates to come join their academy. Yeah.
Wow.
Yeah. Sorry, I should have booked a larger room. But I think it's nicer this way. There's more seats in the front. I'll try to get some more seats. But without further ado, let's have Lidong give his talk. Okay, so over to Lidong. Thank you for
coming. Yeah. So. Some of you may already heard that Alibaba has this R&D Singapore center here, right? We start this center in the end of 2017. So now we have two direction, and I'm leading the NRP group. So my great honor to have this opportunity here to share with you guys some of my previous research. This is the first time I'm presenting these slides. I just finished this version last night, so I'm may not be quite familiar with the whole slides. It's quite long. It's 68 pages. So I try to finish it as soon as possible. Otherwise, I run out 3 p.m. So some advertisement about the Alibaba DAMO Academy. Yeah, we set this DAMO Academy in October in 2017, and we have DAMO is the first letter of those 4 words, and we have 4 goals for setting this DAMO Academy. We want to outlive Alibaba, and also serve 2 billion people all over the world, and also use the technology to solve the challenge of the society. And we have we have 5 research areas and 14 labs. Here we have 4 different departments. I'm with the Machine Intelligence Technology Department, with the NLP lab. We also have speech, vision, decision, and city brain in this MIT department. And also we have 4 different other departments, in total 14 labs. This is the Machine Intelligence Department at DAMO. Those major areas in artificial intelligence, you can find all those major research areas in artificial intelligence. And the NLP R&D at Alibaba, actually we have about 100 employees in 6 different places, Singapore, Hangzhou, Beijing, US, in Silicon Valley, and New York. We have about 120 employees, and we are supporting the whole NLP basic techniques for the Alibaba group. And our Singapore center was started at the end of 2017, and particularly we have 2 teams in Singapore. One is speech, and the other is NLP. We have special interest in those local language processing like Indonesian, Malaysian, to support the globalization of Alibaba. And also, Ali NLP is a very big platform. Ali NLP, the major NLP platform in Alibaba, we're supporting about 350 business scenarios. And in last October, we have about 1,000 billion API calls per day. 1,000 billion API calls per day. And now it's more than 2,000 billion. This is a pretty big number. And this is the architecture of the Ali NLP platform. You can find all those basic NLP techniques here. And also the machine translation. Actually, with the globalization strategy, the first challenge for Alibaba is to translate those product descriptions in Chinese or in English into local language, like in Thai, in Vietnamese. And if we call those translation API from Google, on one hand, Google's translation is not tailor-made for e-commerce. The quality may not be good. More importantly, we need to spend a lot of money. I skip those demos, save some time. So we come to the technical part of this talk. This talk will cover some of my previous work, basically joined with my Indian students or students in my PhD boss group. As some of you may know, text generation is a very long-standing topic. In the traditional way of text generation, there are mainly two tasks. One is what to say, and the second is how to say. For example, you want to generate the text for a weather broadcast. You need to decide what to say, whether you talk about the temperature, talk about the wind. And this is the first task. And the second task is how to say. Basically, in traditional text generation system, you will organize these two tasks in 3 steps. The first one is content selection. The second one is the macro and micro planning. And the third one is the surface realization. So in the area of deep learning, after we have encoder-decoder architecture, we have more power to do more complex text generation tasks. This can reduce the manual efforts to design those templates or to do this content selection, and also this architecture allows us more flexibility to generate the surface form for text, and also increase the fluency of the generated text. Can also take more types of input, for example, the text, the music, and the image or video. But you may notice if you are doing some text generation with NN techniques, it's still a little bit risky to deploy application with these techniques because your generated text is not fully under your control. Because of the training data, the model may learn to generate something that you don't want. So, but this will not hurt this text generation with a model as a good research topic. So in this talk, I will cover some of the text generation research in this in the first 4 topic. The first one is text summarization. As a long-standing research topic, text summarization has about history of 2 to 3 decades. And the second one is text generation in the QA or chatbot. And the third one is text editing, for example, the sentiment transfer, formality editing. And the third one I will cover, the first one I will cover a little bit is generate text from knowledge-based triples or story generation. So in traditional text summarization, we basically have two settings. The first one is the single document summarization, and the second one is multiple document summarization. In the second one, you are given a set of documents discussing the same story, for example, a news event, and then the output should be a short summary talking about this news event, say in 100 words or 200 words. And in general, traditionally, we have three methods. The first one is extractive. We just extract some sentence from the input documents and to order them as the summary. And the second one is compressive. After you extract the sentences, you want to delete some redundant words or phrase. And the third one is abstractive. Abstractive means we want to mimic the way of a human being writing summary. So I will talk a little about the abstractive way. So the goal is to generate summaries just as the human does. After we read a story, a news story, we have our own way to write a summary. But the bottleneck is this way of summarization needs natural language understanding and generation. So before the time of deep learning, there are not many researches on this. Here is one work I was done in 2015 in a traditional way of generate abstractive summary. We were working on more fine-grained syntactic unit, work on noun phrase or verb phrase, based on the observation that, for example, we have a sentence, an Armed man worked into an Amish school. In this sentence, we can break it into a noun phrase and a verb phrase. An Armed man at the concept, and the fact is worked into the Amish school. So after breaking the sentence in this finer granularity, we can have more room to generate new sentences. Let's see how we do that. So the first component is to extract phrases from the sentence. For example, in this long input sentence, we will extract the noun phrase and verb phrase. We go down to the constituency tree to the second level to extract those noun phrase and verb phrase above this level. That means we will get those five phrases, right? And the first one is a noun phrase, I'm the man, and the second one is a verb phrase, the remaining part of this sentence from here. And the fourth one is the sub-verb phrase under this verb phrase. Walked into Amish school and sent the boys outside and blah blah. We have these four phrases here. And the next is how to generate this summary. We define a relation called compatibility. Compatibility means this noun phrase and this verb phrase can form a sentence. For example, an armed man and walked into Amish school. They come from the same sentence, so they are compatible. They can form a sentence. In addition to those NP and VP from the same sentence, we will also generate some other alternatives. For example, this NP will find a set of alternatives by coreference resolution, and also for this VP, we also find a set of alternatives with similarity measure. And in that way, we can take this NP and this VP to form a sentence, or we can take this NP and this VP to form a sentence. This allows the room to generate new sentences. So this is after the compatibility relation is detected, we will have this phrase-based content optimization objective. Here we have the okay. By the way, if you know text summarization, one important concept called ceiling score. That means you will compute the ceiling score for a sentence or phrase or word, and then according to this ceiling score, you can select the important ones. Here means the setting score for non-phrase, the setting score for word phrase, and here means we penalize the redundancy if two non-phrases are selected at the same time, they will be penalized with coefficient. So this is for the salience calculation. This is for the diversity. We penalize the similar ones. And how they selected non-phrase and word phrase according to this objective function can allow us to generate new sentence. We achieve this by using more constraints. This is the objective of these ILP problems, and we have a set of constraints. Basically, the first constraint said that among those selected noun phrase and verb phrase, they should be compatible to form sentences. These two constraints say that. And the third one is recall that in the verb extraction, some of the verb phrase have come from another high-level word phrase, right? This constraint that we will not select both of them at the same time. We select the super one or the sub word phrase. And we have more constraints like we can constrain the number of the sentences in the summary, and also we can constrain on the length of the summary. And also more, say, we want to avoid short sentences and also avoid pronouns. So with this set of constraints, we guarantee that the selected noun phrase and verb phrase can compose new sentence as summary.
Quick question. You said you avoid pronouns, but in fluent text, for multiple sentences, sometimes it's good to generate a pronoun or a determiner phrase like the company instead of IBM or Alibaba, right? So is this pronoun avoidance or specific to just the first sentence or for all of the sentences in the summary?
Yeah, because in the generated summary, we will merge the verb phrase for the same subject.
Okay.
That means for a person name, we will merge out the verb phrase under the same sentence. Yeah, basically we don't need to mention this guy as he again in another sentence.
Okay, so you compose the verb phrases rather than making multiple sentences with the same subject.
Yeah.
Okay.
Yeah. And this is the summary generated from our system. Basically, the first three, we have 6 sentences in the summary, number 1 to number 6. And the first three, number 1, 2, and 4, they are compressive. That means we extract these 3 sentences and delete some redundant phrases. And the third one is a new one. The third one basically merge these 3 sentences. Yeah, this new sentence is generated from these 3 input sentences to merge the word phrase. So after we have these powerful encoder-decoder frameworks, this is typical sequence-to-sequence model. After we have this kind of models, we start to have more powerful tool to generate abstracted summary. This is why text summarization, this direction, say 5 years back, almost dying. And after this sequence-to-sequence model, more and more people think that, okay, we can do some new research on this text summarization task. This is the work from Stanford. They basically use the point generator to generate summary. Okay, by the way, for text, for abstractive summarization with neural network, it basically takes input of a single document, cannot handle multiple document summarization. Maybe cannot handle it well now. For example, you have a news story and 10 news report on this story. you cannot put all of them, say, as a long document into the sequence-to-sequence model. Basically, it will not perform well. This is a pretty simple architecture. You have the encoder here, and also the attention here, and also a pointer network to add those attention score on the final distribution. Basically, those NN-based abstractive summarization follow this idea, have an encoder and add, say, copy mechanism, pointer network, and to generate the summary. I also have a recent work on this highline generation task. In this task, you basically give a few sentences of a news, for example, the first 3 or 4 sentences of a news, and then you generate as a headline. This is a typical abstractive setting. We observe that in the headline generated by human, there is some latent structure. For example, Apple sells Qualcomm for nearly 1 billion. And you will have the structure that who Apple, action sue, and for what sue Qualcomm for nearly $1 billion US. So this kind of latent structure should be captured when you are generating headlines. This will help you to generate the typical, readable, and more friendly, reader-friendly headlines. So we propose such a neural network model. Basically, is if you don't consider those Z unit, it's a typical encoder and decoder framework. And with this hidden variable, it's designed to capture the latent topics. And the next one will take the previous hidden variable as the input. In this way, this autoencoder framework can capture the topic flow, say from who to action to what, this kind of latent structure. And in summarization, we also explore some new settings because as a researcher, you may find that, okay, we're in the bottleneck for this setting, and then let's explore a new setting. Maybe we can bring in more interesting works. In this setting, we will not only consider the document, we also consider the comment. When we are reading a news document, there are a lot of users to issue their comments, right? And we argue that the summary you generated should accordance with the reader's interest. Suppose in this good summary, the good summary covers this part of information, and the bad summary covers this part of the information. But according to the comments from readers, we know that this summary actually will be more interesting to the users. We have 2 papers on this. By the way, the paper I put here are from my group, and the paper I put under the headline is other people's paper. So the first part is about the text summarization. So up to now, do you have any questions? Yeah, please.
So I'm wondering, have you tried combining the traditional linear integer program approach or rule-based approach with neural network approach?
Not yet. Yeah, might be a good direction.
Yeah, how do you evaluate your abstractive summarization output?
There are basically 2 ways. One way is to calculate the red score or blue score against the ground truth summary. This is some kind of word overlapping. You count word overlapping. And the second way is manual evaluation. Yeah, to read if the sentence is fluent, if the grammar is correct. It's basically 2 ways. Yeah.
Right. So your work is evaluated on both kind of both ways, both automatic and also by humans?
Yeah, both ways. Yeah.
Is it possible to propose more comprehensive automatic evaluation matrix on the summarization? So you know so for the currently overlap based methods such as Ngram, Blue Score, like that, the evaluation is not so comprehensive, right? So it might cause some false positive and false negative cases. But manual evaluation might not be reproducible.
Actually there is another automatic evaluation method called pyramid.
Yes.
Pyramid basically because in red score or blue score you count the word overlapping, right? You don't consider the ambiguity of the word.
Yes.
Yeah, some of them may be saying the same thing, but the vocabulary is not matched. In the pyramid evaluation, they will match to a sentence from, say, you can think it's kind of embedding. You can match to a sentence from hidden variables. This will solve this problem to some extent.
Yeah, but it depends on how the embedding is get trained.
Yeah, they for traditional multi-document summarization, they have on-the-shelf embedding or some kind of latent topic trained with a large set of document.
I have a question about that variational autoencoder. So during test time, do you use the mean vector as Z, or do you?
Yeah, the mean vector.
You don't do that sampling in the test time.
No. So the next batch of work I will talk about is text generation in QA task. I know some of you are working on QA. So basically we have a few types of QA. The first type, say community QA or frequent asked question. For this kind of QA, you're focusing more about the question. You need to match the question of the user against your question repository, and then with the matched question, you use the answer to answer the question. And the second type is actually reading comprehension is also kind of QA. The difference, you are given a large document as background information, right? And for this kind of QA, you are more interested in extracting or generating the answer. For example, in score, you want to extract the correct text fragment. And do you know this data set for multiple choice QA? This RIS data set. I think for the middle school students from mainland China, maybe also in Singapore or other countries, because I'm from mainland China, in our middle school English study, we will have reading comprehension questions. Basically, you are given a passage and one question with 4 options, and 3 of them is not correct, and you only have one correct answer. You need to choose among these 4 answers. This data exactly come from the exams in mainland China. And also you have KBQA. For example, you want to generate, given a question, you want to retrieve a triple from a knowledge base, and with the object at the answer. And also in Alibaba, we have a lot of product QA application scenarios. For example, you are given the key attributes of the product, and also some product description and user reviews. When a new user comes with a new question, how to answer this question with the information you have. And other type of QA like visual QA from image or video. Actually, a lot of interesting research work in the big picture of QA regarding text generation. For example, in this work in 2016, this is a very early work called generative QA. That means when you are asking this question, how tall is Yao Ming? You will retrieve a triple from a knowledge base first, and then you want to generate this answer according to the knowledge you got from the knowledge base. This is their this is their architecture. Basically, they interpret this question as the short-term memory will be used here, and also they use this short-term memory of this question to inquiry a knowledge base as long-term memory. For example, how tall is Yao Ming? You will get those three triples. These three triples, and then you reformulate these three triples into a kind of memory. Basically, different terms with probability. And finally, you will merge this short-term and long-term memory to generate the result. But here, the one obvious limitation is that you may not get correct triples from knowledge base, right? One reason is the knowledge base may not have this knowledge. And the second reason is the query may not be well matched with the correct triple. So, and the other limitation is can even make mistakes to select terms from the long-term memory. For example, may select other terms, say Yili or Shanghai, to generate the result. I'm quite familiar with this Sparkle language. Any guys familiar with Sparkle? Okay, good. Because Sparkle is a typical query language to query the triple knowledge base. For example, for this question, who produced the most films? And you can generate a query like this. It's a query quite similar to SQL, right? You select a variable y, where, satisfy these two conditions, and the result is ordered by the count of x. X should be film, right? And you take the result from offset link, and you only take one. That means you will get a list of film director, and you rank it in the descending order, and you will get the top one. That one should be the guy produced the most film, right? So I put this work here is because in the previous work I mentioned that you may not be able to retrieve the correct triple, right? But can we generate this Sparkle query from this input question? If we can, this will help us to retrieve the correct triple from the knowledge base, right? Actually, there are already some research to generate this kind of not Sparkle query, but SQL query from free text to generate SQL query. So this may also be an interesting topic to explore. And the next type of QA I mentioned is multi-choice question. This is an example of the multi-choice question. You can take some time to read it. In each question, you have one correct answer, and the other three we mention as distractor. That means they try to distracting you from the correct answer. Now the state-of-the-art system for this kind of multiple-choice QA is 95%. 59%. And if you consider the nature of this data set, this no much better than random guess. Because in this risk data set, about 30% is very simple factual questions. You can answer this question similar to the score question. You extract a fragment at answer. And then in the remaining 70%, among the four answer, you can randomly guess one, right? And you get a fixed ratio for correctness. And if you plus two, these two, 50% and this 25%, almost 50%, right? And another experiment I did before is if you only give the system the first three sentences, you only give the first three sentences as input for the system to learn how to answer these questions. The performance is not much worse, only 2 or 3% below than using the whole passage. right? This is why I'm saying, yeah, not much better than random guess lah. This is very interesting. Still some researchers keep working on it. I hope they can get better result. And also, this data, another interesting point is this data have a lot of very difficult questions like this. So what's the best title for this article? And what do we learn from this article? Yeah. Do you think the network can answer this kind of question? So I was not working on solving these questions, but I was working on generate these distractors. So my idea is, so the setting is like this. Given the article and the pair of question and its correct answer, my idea is to generate those wrong options. So the motivation is this will have to prepare a larger set of multiple choice question answer data set. And another motivation is this generate distractor may be helpful. Can also help the instructor to prepare the question paper for the students. And more importantly, these distractors may be useful to bootstrap those existing systems, because we already observed that in this work by Yang Zhilin from CMU, we already observed that for the squad questions, the automatically generated query pairs can help to upgrade the squad performance. Yeah, maybe for the risk question dataset, we can also achieve the same research. So then our first step is to automatically generate these distractors. Yeah, again, the encoder-decoder framework, and looks like a little bit complicated. Here we have a hierarchical structure because the input is a long passage, a few paragraphs, tens of sentences. So we cannot encode this long sequence with one typical encoder. This is why we have a hierarchical encoder. Here is the input sentences, sentence 1, sentence 2, and so on. And we will encode each sentence with LSTM. And then we take the last forward backward hidden state here, and with another LSTM to generate to generate the overall representation for the package. And we have a static attention. Recall that in this problem setting, we have article, question, answer to generate the distractor, right? And the distractor should not be the same with the answer, right? And the distractor should also be related to the question. Otherwise, this distractor does not make sense. And with this static attention, we want to upgrade the importance of those sentences that are related to the question, but not related to the answer, and surprise those sentences related to the correct answer. This is the way. This is why we design this static attention. And this for the dynamic attention, we want to emphasize the sentence that is important to generate the current distractor, and also to emphasize the important words in the sentence. And finally, we combine this three attention: the static attention on sentence, the dynamic attention on sentence, and also individual attention for each word in each sentence. Do you have any question about this architecture? It's a little bit complicated. Yeah.
So do you do any experiments to show how the performance is when you tune how related the question and the distractor has to be? Because you can vary the difficulty, right? You can say, I want to make this an easy question, so I let the semantic distance be very far, it's okay. But I also can make the distractor very similar.
To the answer.
Yeah, and then it'll be a harder question. So in previous work, we've done the same thing in our unit.
Yeah, we don't have this difficulty control for distractor generation.
Okay.
After this, I will show another work on question generation. We have this difficulty control.
Okay,
Yeah.
great.
And this is the data set we used. Basically, we prepare our experiment data from the RIS data set. In this RIS data set, we have 27,000 articles. And for the English examination of the Chinese students from grade 7 to 12. So for the 12th grade students, the question can be pretty tough. And also we exclude the travel distractors. Means that if the distractor have no semantic relevance with the article, yeah, it does happen. Some of the question have very random distractor. You don't know where this distractor come from. It can be excluded very easily. And I'll not show you the figures. I will show you this case study. This is a quite long passage with 17 sentences. And for the first question over there, its correct answer is about this sentence 9. The correct answer B, finish the course, come from this sentence. Our static attention can emphasize the sentence 11, sentence 13, and sentence 14. Actually, those 3 ground truths distractor come from these 3 sentences. And for the second question, the correct answer D come from this sentence. You can see that the static score is also smaller because we don't want to generate the correct answer as distractor, right? And also the static attention emphasize all this sentence for the second question to generate distractor because this sentence need some inference capability, need to understand this whole fragment of text. This is the work on distractor generation, and yeah, I encourage some of you can try if these generated distractors can help to improve the performance of this multiple choice question answering. Yeah, and the next research area I want to cover is question generation because it's also pretty hot these days. I also have one work on this. Let's skip this. Yeah. In this 2 work, the first one is from Claricati. They generate questions for the squad dataset. In the first work, the setting is pretty simple. You're given an input sentence, and then after encoding, your goal is to decode the question. You can see the obvious limitation is that you don't know where to ask about, right? You're given a sentence, and you don't specify which fragment you want to ask about. Then the decoded question could be sort of random because you are not specifying which part of the sentence you want to ask about. And later on, this work solved this problem by considering the answer. Here, they use additional embedding to tell the encoder where is the answer in this sentence. And also they use some lexical feature. In this work from my intern students, we is under review, haven't been published yet.
Oh.
We consider how to control the difficulty of the generated questions. Although, if you are familiar with the scored question, you may think all these questions are pretty simple for human being, right? Actually, it is. I don't know why in the leaderboard the upper bound for human performance is not 100%. Even not cannot be 100%. Maybe 98% should be fine, right? Yeah, it's pretty simple question for human being. But for networks or other methods, not that simple. Among these three questions, you can take a look at the first and the second. They're pretty simple. The first and second question are pretty simple. But the third one is not that straightforward. The electric guitar is often emphasized, blah, 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 and as a solo lead instrument. And the question is, what instrument is usually at the center of a hard rock song? And we human can know that the electronic guitar, because here is mentioned as a solo lead instrument. Somehow you need to match that at the center of a hard rock and as a solo lead instrument. You need to match these two, right? So our goal is how to control the difficulty of the generated question. So then the task is like this. You are given a sentence and a text fragment in this sentence. For example, the electric guitar is the text fragment that you want to ask about. And then you are also given a difficult level. Suppose we have two levels, easy or hard. And what kind of question you can generate. This task is pretty challenging because I guess you have no idea how to do that, right? And it's pretty challenging, and we also had a tough time to do that. Because no existing QA dataset have difficult labels, right? And also for a single sentence and an answer pair, we want to generate questions with different labels. For example, easy questions or hard questions. And there's no metric to evaluate if the generated questions is difficult or hard or easy. So our first step is to prepare the data. We have two difficult labels, easy and hard, and we prepare the data like this. We employ two reading comprehension systems, the RNet and BDAF. And then for a question, if both systems can answer this question correctly under the metric of exact match, and this question will be labeled as easy. And if both of them cannot be answered, labeled as hard. And then the remaining questions are excluded from our dataset. Finally, we get this number of easy or hard questions. You may think that, okay, this is not a difficulty criteria from a human being, right? We are still using RNet or BDAP to measure if this question is easy or hard. Yeah, you are correct. Here we have some further investigation to show if this way to annotate the data is reasonable. In this paper, they manually labeled 100 questions by analyzing how many skills you need to answer this question. They define, I forgot the number, about 10 or a little bit less than 10 skills. For example, the correction resolution and some basic inference skills to answer the question of this score data set. And here we have questions according by DAF, RNet, and our proposal. Among these 100 questions labeled by this work, 64 is labeled as easier by by DAF, and 70 labeled as easy by R9. And we have 55 here, and we have 21 here. Because we exclude some of the sentence, right? Some of the question. That means we only, among these 100, our data set only cover 76 of them. This is why the number is not 100. And we calculate the average skills needed to answer each question. And we find that for our data set, for the hard question, we need 1.8 skills to answer. And for the easy one, we need 1.16. But for R9 and BIDAF, for the hard one, number of skills needed is smaller. That means our data set can differentiate easier and harder questions to some extent. Cannot be perfect. Again, a new network framework. In this paper, we explore an interesting intuition or an interesting finding. From this table, you can see that the first line, average distance of a question word, distance to the answer word. For example, you have a electronic guitar, blah 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 blah. The sole instrument in this sentence, the answer is the electronic guitar, right? And in the question, some of the words come from this sentence, right? And we will calculate the distance of those question words to the answer word, the electronic guitar. We found that for the easier question, the average distance is 7.67, and for the hard one, it's 9.7. That means easier questions are using more words from the sentence that are close to the answer, right? The distance is smaller. But for harder question, the question is trying to use the words that far away from the answer in the sentence. And this sentence, this line is for contrast. For all the sentence word, the average distance to the answer word. Say for this entire sentence, you calculate the average distance of each sentence word to the answer. The average distance is roughly 11 for both easy and hard question. That means this phenomena we can explore to generate difficult or easier questions. Here we basically, actually we have two ways to explore this. We can ignore the difficult level, right? If you compare these two numbers, you don't consider easy or hard, you only contrast these two numbers. There's still quite a large difference, right? We can directly train an embedding for the positions, for the word position, right? This will already help us to generate better questions. And if we differentiate the difficult labels, for example, we can train an easier position embedding or hard position embedding. And then according to the question you want to generate, you will pick the correspondence embedding from this table. So these two types of way of using this position embedding. You have only one position embedding. You basically explore the question word proximity hints. And if you have two individual embeddings here and here, you are exploring the difficulty level related proximity hint. And then we also have a global difficulty control, basically two embedding vectors. And for easier question, you will use this embedding. To generate a hard question, you use this embedding. Yeah. Do you have any question regarding to this architecture? Okay. And this is how we evaluate if our architecture works reasonably. It's also not that straightforward to do this evaluation. So for the first evaluation, we think that for easier question, suppose our system are generating easier questions, and then the R9 or BiDAF systems should perform better, right? If we give the control variable is easy, and those RC pipelines should perform better. If we give the we give the control variable hard, and the generated question should be difficult for these RC pipelines. And we did observe this difference. This is the best pipeline of our framework. And for the easier side of the question, we can see that the R9 and BiDAF performance are the best here, right? And for the hard question side, we can see that the R9 and BiDAF performance are the lowest here, right? This can show that our way of generating questions can control the difficulty. And for the second evaluation is so the scores, the performance gap between the original difficulty label and the question generated with reverse difficulty label should be larger if the control capability is good. You can see that this pipeline still have the larger the better, because we are contrasting the performance of one RC pipeline on the original label or with the reverse label. For example, for this easy question set, we will calculate the performance of R9 and BiDAF, and then for the same set of question, we will feed the generator the reversed label. That means to generate a harder question for this set, and then calculate the difference between the performances of the same pipeline on these two sets of questions. And the larger gap means better. Okay, this is a case study. So, for example, for this input sentence, the human-generated question is this one. You may see that it's not a very good question, right? It just replace the answer with the question word. Yeah, sometimes with those crowdsourcing platform like Amazon Mechanical Turk, you do get this kind of now serious worker for you. And the number here means the number in this bracket means the average distance of question words to the answer. And here is the question generated by the baseline. Here is our pipeline. And here is if we use the reverse label. Here we use the label easy, right? Because the ground truth question is an easy question, and we use the easy label. We generate a question like this. And if we use a hard label, we will generate a question like this. You can read it, get a feeling about the difficulty difference. And also, for this electronic guitar example, the question generated by our pipeline is, what's the solo lead instrument? It's quite precise, right? And if we want to generate an easy question, we will give the easier label to this pipeline. And the question is, what's often emphasized? Okay. Yeah, I think I almost run out of time. I still have 20 pages, so I skip most of them, right? Yes. For text style transfer, it's also a pretty popular task in the recent 2 years. This first work comes from MIT by Regina Basline from NIPS 2017. They basically want to rewrite a sentence in positive sentiment into a sentence in negative but should keep the content same, only change the polarity of the sentiment. I'll skip these details, and also this NACO last year interesting paper, and also this one ACL, this last year. I'll quickly go through this work from my intern student. In this setting, each sentence is associated with a numerical outcome. It's a numerical value. For example, the food is terrible. The numerical value is 1. The rating of this sentence, right? And also the food is okay, rating 3. And the food is delicious, rating 5. In the previous works, they set this as a discrete value. For example, this negative, this positive. But here we have a different setting. We use the numerical value as the outcome. And we want to train a model with the capability that given a review sentence and also a target rating, we want to rewrite this sentence by keeping the content, but change the sentiment towards that rating score. This is the problem definition, and this is our framework. We have this part to model individual sentences. It's basically a VAE architecture. We decode this input sentence. For example, the food is extremely delicious. We decode this into a variable y and a variable z. And also, if we combine these two variables, we should be able to reconstruct this sentence x. And also, this variable y is basically a vector, can be used to predict the rating score. This is how we model a single sentence, and also we have this part to model pseudo parallel sentence, because we generate this parallel sentence with the algorithm, so they are not real parallel sentences. These are the losses from the single sentences. Basically, the construction loss, the KL divergence loss, they are quite typical for VAE, and also we have a mean square error loss. That means we want to check if this prediction of the rating is accurate enough. And also we have this pseudo parallel sentence. This is important for our framework. How we generate this pseudo parallel sentence, you can read through this. I will never come back to this restaurant. And it's a pseudo parallel sentence in this one. I will definitely come back to this restaurant, recommend. So we generate this kind of sentence pair in this heuristic way. First, we check if this two sentences with enough, with a lot of overlapped word. And then we will check their rating score. If the rating score is significantly different, for example, this is 4, this is 1, this is 5. If their rating score is much different, then we can guess that this wording overlapping is because of the content part. And this difference, this rating score difference is because of some of this opinion word, like never, definitely, or recommend. In this way, we get this pseudo-parallel sentence pairs. And then with this architecture, we model this kind of pairs. Basically, just contrast the wording difference and connect this wording difference to the rating difference. And also, we want the content vector decoded from these two parallel sentences the same, because we assume that they have the same content, so their latent vector related to the content should be similar. And again, we have the reconstruction loss. That means if you are given the content vector of one sentence in a pair, and you are given the rating related vector of another sentence in the pair, you combine these two, you should be able to reconstruct the second sentence in the pair, right? Because the content comes from the first sentence, and the rating comes from the second sentence, and combine these two, you should be able to reconstruct the second sentence. This is how this reconstruction laws work. And I skip this. I also skip this. These are some examples. Later on, I will send you the slides. I think Professor Ming will distribute this, and you can read through them. Yeah, style transfer is pretty hot these days. At least part of this style transfer papers here. You can see that a lot of last year, right? In 2018, it's a pretty hot direction. And the last part is about knowledge to text. That means you are given some of knowledge from knowledge base or other forms of knowledge. You want to generate the text describing this knowledge. And one famous data set called Wikibel. Anyone know Wikibel? Wikibel is a data set from this paper. Basically, you are given the first few sentences of this people's Wikipedia article, and also you are given the info box of these people. You want to generate the first few sentences with this info box. This is why it's called Wikibel. And another one is Wikitable from this paper last year. You are given the table, say, describing the financial report of company, and also specify that you should generate text to describe a particular region, particular lines or columns, and then your task is to generate text to describe this region. Another task from knowledge to text is WebNRG. This is the challenge called WebNRG challenge, creating text from RDF data. RDF, you can simply think that RDF is triples. Wiki just like free-base triples. For example, the input triple can be like this. This guy birthday, birthplace, and this guy occupation, and then the task is to generate this text. This text including these three triples. And I also have work for this problem under review. The idea is also to capture the hidden topic flow in the generated text. For example, this part is about the career of this guy, and this part describing the birthday information, or maybe birthplace. This paper is under review as well. So, finish the technical part. That's good. And the open question is because of the black box nature of the generic encoder-decoder architecture, so there could be this kind of errors. The reference error, the inter-sentence incoherence, and a lack of fidelity to the source material. Yeah, this will happen. It depends on the task. For example, for machine translation or summarization, this problem may not be that serious because you have a full information, the input. Your output should be well aligned with the full information, the input, right? But for knowledge triple to text, or for answer generation or question generation, the situation is much different. And one idea, maybe we can try to bring back the advantage of the convention methods. For example, to learn sentence template with the neural method, or to learn a macro planning with the neural method. Yeah, this is how to combine the traditional method with the neural network. Yes.
Like I said earlier, both the slides and the video for this talk will be made available. But we do have a little bit of time for questions, so I'll open the floor for questions from people inside the room as well as outside the room. So, Lidong.
So, the state-of-the-art sequence-to-sequence model for generating abstractive summary, how does it compare with prior state-of-the-art method for doing extraction, lifting sentences to generate a summary?
If we compare, in general, if we compare those blue square or red square the abstractive way with neural network can have some advantage. Yeah, because more or less the distracted sentences will bring in some redundancy. In neural network, we have the flexibility to generate new sentence. This sentence can be trained to only include those salient words or phrase. Yeah, in that way, say like right score, the abstractive way with neural network could be better. But if we evaluated the in the manual way, for example,
Humans.
yeah, by humans, if the fact in the summary is 100% compiled with the news, I think the extractive way should be perfect almost. Maybe lack of some important facts, but the extracted sentence should convey exactly the facts describing in the news document. But for abstractive way, this cannot be guaranteed.
My question is like, if today I want to build a summarization system, like, what method should I use?
Extractive.
EXT.
Extractive, yeah. Even those deploy system in the company, we keep using those simple methods. Yeah.
So last year's AC Multimedia Best Paper is about giving a picture, and then the system could generate actually a poem. And my question is, from your expertise in this area, is it realistic to expect that given some constraints, we can actually really generate a long paragraph, like a complete lyrics of a song?
For poem generation or 对联 generation, if you're Chinese, you know what is 对联, right?
Yeah.
There quite a few research for doing that from Peking University or Tsinghua University. Personally, I don't think this generated 对联 or poem can really tell you the sense, just like those from the traditional poem from those famous writers. Those generated ones just use the words in correct pronunciation and make the 对联 or the poem make you read it. When you read it, you feel comfortable because the tones are correct. But if you consider the back-end meanings, I don't think make much sense.
It's meaningless, basically.
I think most of the time I think so. Yeah.
How do you make sure the question that you generated really have the answer of the original answer that you want? Maybe the question you generated doesn't match its answer. The question generated.
You mean how to guarantee that this question is asking about this answer, right? We will specify in this sentence we want to ask about this fragment. Yeah, this is what we usually do now. In the first work from Claricati students, they just give the whole sentence as input without specifying which fragment you want to ask about. In that way, you cannot control where this question is asking about.
Follow up on the question, the evaluation of question generation, the difficulty and easy questions. You generate easy and difficult questions, right?
Mm-hmm.
So how do you know that the difficult questions which the RNet and VIDA scored less, how do you know that the difficult questions are actually correct? How do you evaluate that, whether the questions generated actually make sense?
We also evaluate this from two perspectives. One is see if the R9 or BETA can answer this question. But from this perspective, there is no guarantee that the generic question itself is correct, because we are only evaluating if the extracted answer is correct. And we also evaluate those questions manually.
One last question over here.
May I ask, do you actually deploy these technologies in your e-commerce business? Because like like where can we find like how to use this? For example, like do you deploy this on top or team or do you summarize the description to form a title? Or?
Yeah, for as I mentioned, if you use those methods from research papers to deploy a system, probably your boss will be very angry. You need to combine it with very heuristic ad hoc methods. For example, for product QA, you cannot directly use those generated answers. You need to have another pipeline, maybe very simple classification, to determine if this generated result can be used. If no, you have another branch to generate result with a very heuristic way, maybe template-based way. This is usually how in a company to combine some of the research algorithm with the online product.
So do you actually use this technology to form the title like currently? Because recently I have noticed that like when I'm browsing the top of page, I see less like random like fragments of words like free shipping inside the title itself.
Mm-hmm.
Yeah. So are you actually deploying this technology to
Top of title is quite complicated. It could be quite long, and the retailer or the seller, they put every important keywords for SEO, because Taobao also have a policy to rank those products for each search query. They put all important keywords they think in the title. Yeah, because title words will be give higher score, right? Yeah. Some of the buyers, they want to search, free shipping, swimming glasses, and then this top item will get higher ranked.
Okay, so I'd like to thank our speaker. Thank you for coming. A very good turnout because I think it's still the first week of class, so everyone's still free. Okay, thank you for coming very much.
Hope you keep coming for the entire semester, right? Not only the first week.
Yes, that's always a challenge for both faculty and students. We'll advertise them later. Both the recording will probably be on YouTube as well as slides. Yeah.